Okay, so I'm going to cover chapter 14, which is the entire universe. Of course, we're only going to hit some highlights. So, the night sky, when you look up, you see at most, with the unaided eye, about 4,000 stars. This would be in a very, very dark region. But there are literally billions upon billions of stars. There are at least 100 billion stars in our own galaxy, the Milky Way, and there's probably over 100 billion other galaxies in the known universe. So there are tons and tons of stars. Of course, we can trace back to ancient civilizations looking up at the stars. Here's a picture of Stonehenge in England, where this was an observatory, or at least we think it was, because it lines up with the spring equinox, and this is something that was important to ancient peoples all over the world, and sometimes we have these relics. Stars appear as point sources. That is, even with the most powerful telescopes that we have today, the stars are just a single point of light. For example, when you look at a planet with a telescope, or even a pretty good pair of binoculars, it'll actually look like a round object. So it's extended. It's not just a single point. It's actually extended. And of course, I should mention here that the planets, the 8 planets that we have in our solar system, all reflect the light of the sun. That's how we see them. And getting back to stars, of course, the reason that they're point sources is because they're so incredibly far away. And when the stars pass through the atmosphere, for example, the starlight, since it's a single point, if there's any turbulence in the atmosphere, where the light basically can bounce around a little bit, that's what we call twinkling. That's just an atmospheric effect, and most telescopes these days, modern telescopes, with the aid of computers, can almost eliminate that. Of course, space telescopes, you don't have to worry about it at all. And as I said, stars are extremely far away, and so what we do is we use, there's actually a couple of units that are very common. One is called a parsec, and that's the distance that light is let me just say that's one of the units, and in 1 parsec there are 3.26 light years. And so what is a light year? A light year is it's 9.5 times 10 to the 12 kilometers, but what it actually is the distance that light travels in 1 year. And this is probably the most useful unit of measurement in astronomy today. I mean, we measure using light years to nearby stars, to galaxies, to really the edge of the universe. And so, when we say that the universe is about 13 billion years old, that is because the oldest light that we see is about 13 billion light years away. So, and also within our galaxy, the nearest star to us is a little more than 4 light years away, and that's just the nearest one to the sun. Our galaxy is about 100,000 light years across, and the nearest large galaxy to us, called Andromeda, is about 2.5 million light years away. So the light that left Andromeda, left about 2.5 million years ago. This is really going back to ancient peoples and the way that we, of course, we, for the longest while, we could only observe the night sky from the Earth. It's only very recently that we could send a spacecraft up to make observations, astronomical observations. So there is this thing called the celestial sphere, and it's just an imaginary sphere that surrounds the Earth. That's all it is. And there is, of course, a celestial equator, which is just the projection of our equator, the Earth's equator, out into space. And since the Earth is tilted with respect to the sun by about 23.5 degrees, the north celestial pole is also tilted because it's an extension into space of our North Pole. And the same thing with the South Pole. Now, the fortunate thing right now in our history, the North Pole, as you extend out into space, is actually really close. It's like around a degree away from a very bright star called Polaris. So Polaris is the North Star. There is no such star in the southern hemisphere if you extend the South Celestial Pole out into space. There just doesn't happen to be a bright star right there. Okay, of course there are stars, but this is what you would see. This little picture here is showing a kind of a time lapse of looking at the north or the south. All right, let's see. The celestial meridian is your east-west location. Imagining, well, you're not imagining. You are on the surface of the Earth, and you're looking out into space. Of course, that you can only look and observe space for, half of a day, roughly, because when the sun is in the sky, you can't see any stars. Usually, mind you, you can see them if there is a solar eclipse, but that's a pretty rare thing. So the stars will appear to rotate. They move from the east towards the west. If you just sit there and you look at the stars and you spend a little bit of time outside, you'll notice that those same star patterns that were, further in the east will be migrating towards the west, and they make big arcs in the sky. And of course, the only reason for that, the reason for the east-west appearance of the stars and the moon and the sun, for example, that they're all rotating apparently clockwise, is because the Earth is rotating in the opposite direction. So the Earth is rotating from the west towards the east. Okay, and so that's really what you're seeing along the celestial sphere. All right, now let's talk about the stars in particular. The stars are very, very dense, extremely dense. And here's the thing: it's really interesting. They're extremely dense, and yet they're still gas, right? And they're much more dense than, for example, any of the solids that we find on the Earth. Now, the reason that they stay a gas is because because of the power source of the stars is what we call fusion. Now, fusion is a nuclear reaction. It's a reaction that only takes place in the center of a star, at its core or its nucleus, and what basically the thing that's happening for most of a star's life is it's turning hydrogen into helium. So it's doing it on a tremendous scale, and these are basically this is the same kind of thing that we figured out how to do here on Earth, which we don't have control over these things. They're basically called H-bombs or hydrogen bombs. All right, so that's what's going on in the center of the sun. Our star is an average star. It's an average size star. It is a medium temperature star. It's not not really one of the hotter stars. It's not one of the cooler stars. The stars all come from we find these regions between the stars, which is what we would call interstellar space. We find these regions filled with gas, mostly hydrogen and helium. Okay, so the hydrogen is about roughly 70%. The helium is roughly 71%. The helium is roughly 25% or so. And so you have these giant clouds of hydrogen and helium, and perhaps there's a passing star, or there's a star that went supernova, exploded, and what'll happen is it'll collapse some other region where the gas and dust exist, and you'll have new stars forming. And before the star really kicks on, before the fusion process. So a star is only, it's only a star when the fusion process takes place. But there are objects that we can detect. You can't see them directly in the visible part of the spectrum, but we can detect them in other regions of the electromagnetic spectrum called protostars. And all these things are extremely hot, but the reason that they're hot is not because of fusion, not because of converting hydrogen into helium, but because matter, this gaseous nebula, is still falling in towards the center, and of course, the gaseous nebula will have other things that will surround the center. Then eventually those will become the planets and so forth. But let's just stick with stars. So the core is the most dense region. It is, as I said, much greater density than any solid on Earth. So nuclear fusion is what takes place at the very center. And there is, after the fusion takes place, there are gamma rays and X-rays produced, and this region around the core, this region here that I'm pointing to, is called the radiative zone, where radiation, basically photons of light, carry that energy. And you might think that this would be almost instantaneously, but some estimates, some calculations show that the photons don't really travel very far before being absorbed and then re-emitted, absorbed, re-emitted, and that takes time. And it takes a long time for the light, for a single photon to reach the surface, for example. Some estimates put it at like 1 million years, but it depends on the average, the temperature and the thickness of the material. Anyhow, let's see. So after that, there is what's called the convective zone, and the convective zone is just normal convection, hot material rising. So the hot material rises towards the surface and then is released as photons. All different photons right at the surface. The surface of the sun, our sun, of course, our star, is roughly 6,000 Kelvin. And just to put that in perspective, it's about 10,000 Fahrenheit. So that's right at the surface. And notice the sun has these dark regions. Those are the dark spots, and these are basically regions of very strong magnetic fields which poke out from the surface of the sun. And basically what's happening there is this convective zone is not able to release all the heat. And so the reason these things appear dark is because they're a little bit cooler than the surrounding surface. Not very much cooler. They're maybe 1,000 Kelvin cooler. All right. The sun is converting hydrogen into helium, and it actually, when it does that, when all the stars do that, they're following Einstein's famous equation, E equals mc squared. So the energy comes from mass. So, as it says here, about 1.4 times 10 to the 17th kilograms of matter is converted into energy. And this is a tremendous amount, but the sun is extremely massive, and so it's been converting hydrogen into helium for about 4.5 billion years, or roughly 5 billion years, and all estimates, all calculations show that there's at least enough hydrogen in the core, in the center of the sun, to last for another 4.5 to 5 billion years. All right, we'll start